Okay, so we're going to move on to work with natural logarithms. So just a quick reminder, we call these ln x, and that is log of base e. So if we've got log of base e, we don't write that, never seen that, we write ln. Okay, now I'm going to start with considering the sketch. You know I always love my sketches. Okay, so what I've done is I've sketched out y equals e to the power of x, which goes through the y-axis at 1, and then it turns off. Okay, obviously we've still got our asymptote at y equals 0. Now, if I want to consider the sketch of ln x, what I'm going to think is I cannot have x to be negative. So what I'm going to have is I'm going to have actually a vertical asymptote, okay, where x equals 0, and x can't be any value there on this side. Okay, a really important value is that when x is 1, I get that y is 0, because ln of anything of 1 is 0. And what we actually find is that as it's below 1, it shoots off down to negative infinity. And then up here, it's going to consistently grow. So you see it's going a bit down. I'll make sure that I didn't draw that in the exam. I want to show that it always goes up, even if it's very, very slow growth. Okay, so because it's slow growth, it is always increasing. Now, this graph kind of shows very, very nicely that if we drew this line, let's draw this line here, this diagonal. Okay, so that's the classic diagonal, call it y equals x. Well, it is y equals x. We can see that these are reflections of each other, and that is because ln x is the inverse of e to the power of x. So if I do ln of e to the power of x, that would be the same as e to the power of ln x. And because the ln and the e cancel each other out, they're inverses, that will just be x. Okay, so we're going to use this just to solve a few things, but it's just a good understanding to have. Alright, let's go on to examples. Okay, so we can do this in several ways. Most of it will just go straight to the answer, which I'll write in black. Okay, however, a thought we can have in the middle is that if I take logs of both sides, the natural log, I get ln e to the power of x is equal to ln of 5. Now what we've just said is this cancels out, so we just get x is equal to ln 5. Okay, now most of the time we'll just go straight there because we think log of base e is ln 5, and then we get our x there. Okay, similarly, we can have this middle thought process that if we take e with the power of both sides, the e with the ln x, that cancels out and just becomes x. Okay, so my answer here is x is equal to e to the power of 3. Okay, lots of us just think ln will be base e, so we can go straight to that answer. And I'd probably suggest doing that. Alright, a couple more slightly longer examples. Okay, so there's no new maths here, just making sure that we've seen it so that when you do them in the questions, you're at least a little bit familiar. Okay, so what we're going to do is we're going to rewrite it out so that our power is down and not a power anymore. So I can write that 2x plus 3 is equal to ln 7, considering what we just thought in the first example. Okay, now we just rearrange it like normal. So 2x is equal to ln 7 minus 3, and therefore x is equal to this side, all divided by 2. As it's an exact form, I will do nothing else to that there. Okay, similarly, over here, well, I can't get the x away from the ln unless all the numbers are away. So let's do that 2 ln x is equal to 4. Okay, there's two ways we could do that. We could bring this 2 and get x squared. Or I'm just going to divide by 2. So I get that ln x is equal to 2. Okay, and therefore x is equal to e squared is our answer. Okay, we only have one answer because even if we'd taken the squared here and square rooted, we can't have a negative number as an answer because we can't input a negative into a logarithm. Okay, last example for solving. We have e to the power of 2x plus 5 e to the power of x is equal to 14. Okay, now this is similar to one of the last ones that we did in the previous video, where what we need to spot is that e to the power of 2x is the same as e to the power of x squared. Okay, I've then got plus 5 e to the x is equal to 14. Okay, now this means I do have a quadratic, so just like last time, I'm going to split it into 2 and solve it in 2 ways. With a quadratic, we always need to set it equal to 0. So the first thing I'll write is that e to the power of x squared plus 5 e to the power of x minus 14 is equal to 0. Okay, and I'll solve it the more formal way again first, and then we'll come back to this one and see how we can do it a little bit quicker. So I can say let y equal e to the power of x. Okay, using this equation here, I can see that y squared plus 5y minus 14 is equal to 0, and this is something nice and easy for us to solve. So I've got y, will it be minus 2 and plus 7? Okay, and therefore y is equal to 2, or y is equal to minus 7. Now one thing to note here, we are not solving for y, we're solving an equation with x in it. Okay, so I then need to put back in that e to the power of x is equal to 2, or e to the power of x is equal to minus 7, and we'll solve from here. I'm just going to pause a second and get to this point using this method. Okay, so if we go back to this side, the variable, rather than y, is just e to the x. So what we do is, like we practiced with that 5 to the power of x example, I just put my e to the power of x in my brackets. I then consider the plus 5 and the minus 14, and I get that minus 2 and plus 7. Okay, so setting this bracket equal to 0, I get e to the power of x is 2, or e to the power of x is minus 7. Yeah, now, either way you do it will get you the same marks. It's up to you, whichever you prefer. Now, solving from here, I get that x equals ln 2, nice and simple. However, we have to be careful here. So here, I would get that x is equal to ln of minus 7, but we cannot input a negative number into there. So I wouldn't even bother writing that. This is what we call undefined, or there's no solutions. Okay, just like if we're trying to square root a negative, we can't take a logarithm of a negative. Alright, moving on, we're going to do a modelling question, just involving some ln, and then that's us done for here. So let's read through this question. The temperature, T degrees C, of a cup of coffee after T minutes, small t, so it's different, is given by capital T is equal to 20 plus 60 e to the negative 0.1 t. Okay, when I get these questions, before I read any of the subparts, now there are a couple more than this, we'll just do it bit by bit, I try and think about what this equation means. Okay, so if I just focus in on here, what I've got is t is equal to 20, okay, just by itself, plus 60. Now this is the important bit. I've got an exponential to the power that's negative. Now, if you remember, hopefully most of you do, this means that I'm going to have some sort of decay. So over time, this number here is going to get smaller and smaller and smaller until eventually this basically becomes nothing. Okay, so let's now start to answer the questions. What's the initial temperature? Well, that means what's the temperature when t is 0? If I say that the capital T will equal to 20 plus 60 e to the power of 0, because that's what it'll be, well, that's just going to be 1, isn't it? So I do 20 add 60, and I get 80 degrees C. Okay, what's the temperature after 5 minutes? Again, nothing difficult. Just means that we need to put when t is 5 into the equation. So I say that t is equal to 20 plus 60 e to the negative 0.1 times by 5. We're hoping it's a bit smaller than this. Makes sense, cup of coffee gets colder as you leave it. And also, yeah, if we put it into our calculator, we get 56.4 degrees. Alright, next part. So the third part of the question says, after how long will the temperature be 25 degrees C? So this is talking about the capital T being 25. So let's write that out. So we want 25 to equal 20 plus 60 e to the negative 0.1 t. Okay, we're going to want to find t, that's the time, that's how long it'll be. Okay, so take away that 20, I get that 60 e to the negative 0.1 t is equal to 5. And divide by 60, I'm going to get e to the negative 0.1 t is equal to a 12th. Okay, now pretty alright for us to solve this, we should be used to it now. We're going to say that the power negative 0.1 t is equal to ln of a 12th. Okay? Now if I was being lazy and I just wanted a numerical answer, I could just type that into my calculator. Okay, however, I'm going to look and consider how I can leave this neatly, because sometimes it tells you to leave it in a certain form. So let's have a look. If I want to leave this as neat as possible, I'll say that t is equal to, now rather than dividing by negative 0.1, I'm going to times by negative 10. So I get negative 10 ln over 12th. Now here is where we can do some neatening up, because that 1/12 we can use a power of -1, so I can get t is equal to -10 ln of 12 to the -1, and then I can bring that power down and that'll cancel that negative as well. So very, very nice and neat. We get t is equal to 10 ln of 12. Okay, so that gives you an answer. This will give you the same answer, but it's a nice form. I believe the answer would be 24.8 degrees. Sorry, minutes. Oh, 24.8 minutes. Alright. Last part. Last part is what is the temperature of the room? So this is where that thought that I had at the start of the question of understanding this formula comes in quite helpful. So I'm going to do it the very mathsy way. Okay, but some of you might just spot that it's 20. Okay, but let's explain why. Okay, so the temperature of the room, we think that over time, as time increases, the coffee is just going to become the same temperature as what's around it. So what I want to think is what's going to happen as t tends towards infinity, as t gets massive, as t, even as t approaches 10 hours, it's going to just be the temperature of the room. But if we just imagine the extreme, well, if this happens, then I know that this part here, the e to the negative 0.1 t, that's going to tend towards 0. Okay, so it's that decay model, and if you remember a decay model, oh, something like that, and it gets closer and closer to 0. Okay, so if that tends to 0, if I look back to here, that means that t is going to tend towards 20, because this will just be left by itself, because that will be 0. Okay, so the room temperature must be 20 degrees C. Okay, because that's what it's going to end up being at the end. Alright, and that's it. That's everything on logarithms. We just need to do modelling of curves, which will be your next 2 lessons. It's quite a big topic. It's large mark questions. Okay, so yeah. Thank you.